So, welcome students for the chemistry lecture, and now you are going to learn the thermodynamic derivation of law of mass action. All of you know the law of mass action. It states that the rate at which chemical reaction takes place is proportional to the active mass of the reactant. Okay, the rate at which chemical reaction takes place, it is proportional to the active mass of the reactant or concentration of the reactant. Here the law of mass action states that the rate of reaction is proportional to the product of the concentration of each reactant. If there are more than two reactants, then this law can be used to explain the behavior of exhibited by solutions in dynamic equilibrium. The law of mass action also suggests that the ratio of the reactant concentration and product concentration is constant at a constant chemical equilibrium. Here, the equilibrium constant, it is represented by letter Kc, and this K, it is the equilibrium constant. This C, it is the uh, concentration of a reactant and product for a liquid state reaction, a homogeneous reaction which is taking place in a liquid state. The concentration of reactants and products at equilibrium are constant at a given temperature. Then consider the following simple reversible reaction where A and B are the reactants and C and D are the products. This is your chemical reaction, reversible chemical reaction. A and B are the reactants and they react to form the products C and D. A mixture of products and reactants in a state of chemical equilibrium is known as an equilibrium mixture. When the mixture of reactant and product in chemical equilibrium, then it is known as an equilibrium mixture. There exists a relation between the concentration of products and the concentration of reactants for an equilibrium mixture. This relation can be equated or can be represented as follows. Here Kc, it is equal to active mass. This square bracket, it is called as active mass or concentration. Okay, then Kc, it is equal to concentration of product C into concentration of product D divided by concentration of reactant A into concentration of reactant B. That is the equilibrium constant, it is the ratio of concentration of products divided by concentration of reactant, and it is always constant. Then here Kc is called as equilibrium constant. In this equation, the concentration of A at equilibrium is represented as in a square bracket A. Similarly for B, C and D. And the stoichiometric coefficients of the reactants and products are unit. So we have not represented it here. It has been experimentally observed that equilibrium constant is also dependent on stoichiometric coefficients of the reactants and products. And in 1864, the two Norwegian chemists Cato Wilbur and Peter Wedge proposed the law of mass action as a general description of the equilibrium condition. This mathematical expression holds good for reversible reaction at equilibrium and at a constant temperature. A certain ratio of reactant and product concentrations has a constant value, and that constant value it is we call as equilibrium constant. Then consider another general reversible reaction as suppose we have A moles of capital A reactant and B moles of capital B reactant. Then it reacts to form the C moles of capital C product and D moles of capital D. These are the stoichiometric ratios. Here where A, B, C and D are stoichiometric coefficients for the reacting species A, B, C, D. Then the law of mass action is represented by the following expression. Here K it is equal to concentration of C raised to C into concentration of D raised to D upon concentration of A raised to small a into concentration of B raised to small b, where K is called as equilibrium constant, or it is also represented as Kc. This is also called as the equilibrium law or law of mass action. Therefore, the law of mass action dictates that equilibrium constant at a given temperature is equal to the product of concentration of products raised to the respective stoichiometric coefficients divided by the product of reactant concentrations, each raised to the corresponding stoichiometric coefficient, and this is also known as the equilibrium law or the law of chemical equilibrium. Then the representation of equilibrium constant for a balanced reaction of this type here, according to the law of mass action, the constant value obtained by relating equilibrium concentrations of reactants and products is called equilibrium constant. Okay, then here we can write for the homogeneous reaction involved in a liquid state, we represent equilibrium constant as a Kc, and it is equal to, for this general reaction, okay, A and B are the products, C and D are the reactants here. And in case of gaseous reaction, here we replace C by P, where P it is the pressure, and equilibrium constant in case of gaseous reaction it is represented as Pc raised to small c, Pd raised to small d upon Pa raised to Pa raised to small a into Pb raised to small b. These are the moles of A, B, C, D. Okay, and the ratio of partial pressures of product divided by ratio of partial pressures of a reactant. This ratio gives the equilibrium constant in case of gases reaction. And here we have to derive these two equations in case of gases or liquid state with the help of one-top equilibrium box. And you know, the one-top equilibrium box, these are the a big vessel provided with four uh, semi-permeable membranes. Here we have this semi-permeable membrane is it allows only the introduction of reactant A from this semi-permeable membrane. Then this second semi-permeable membrane it allows only the introduction of gas B, and this semi-permeable membrane. From this we can withdraw the gas C, and from here we can withdraw the gas D. Here with this is the want of equilibrium box, and we have to take such a two big want of boxes, and we have to introduce the gas A and gas B from one box to the another box, and at the same time we have to withdraw the gas C and D, that means products, at the same time from the another box. Okay, this is the want of equilibrium box. It is provided with catalyst so that the equilibrium between reactant and product it is maintained. Such a two big want of equilibrium boxes are taken, and we have to introduce gas 1 mole of gas A and 1 mole of gas B at the same time, and from one box to the second box, and at the same time we have to introduce the gas C and D from second box to the first box. Okay, and with the help of this in the form of Gibbs free energy change, here we have to find the law of mass action. Okay, so see here, this is the first equilibrium box, and the reaction taking place in this first equilibrium box, that is the here we have gas A with partial pressure PA, gas B it has partial pressure PB, then the gas C it has partial pressure PC, and gas D the partial pressure PD in box 1. And in the second box, suppose we have P dash A, it is the P dash A is the partial pressure of the gas A in second box, P dash B partial pressure of gas B, then C dash P dash C it is the partial pressure of gas C, and P dash D it is the partial pressure of gas D, and the introduction or withdrawal of 1 mole of gas from one box to another second box, or from second box to the first, it does not alter or it does not change the equilibrium involved in the reactants and products. Okay, so here, the law of mass action can be deduced thermodynamically as follows. Let us consider hypothetically the two one-top equilibrium boxes or vessels of different volumes, here as shown here. Then the volume of each vessel is assumed to be so large that the removal of small quantities does not change the composition. The box is kept at a constant temperature. The reactants and products of the reaction are in equilibrium with each other, and it is provided with number of semi-permeable membranes through which each component of the equilibrium mixture can be separately introduced or withdrawn. Inside the box, a catalyst is provided to maintain the equilibrium. Then, in each of these vessels, the four species A, B, C, D are always in equilibrium. That means they are in equilibrium condition. Further, consider that each of the four walls of vessel is permeable to only one of the component. Then let the partial pressure of each species in first vessel are PA, PB, PC and PD, and that in second vessel are P-A, P-B, P-C and P-D respectively. Further, it is assumed that all the reacting substances are in ideal condition or ideal gases. And we know the free energy change in isothermal reversible processes is given by here. This is the free energy change. In general, it is given by delta G, it is equal to RT ln P2 by P1, where R it is the gas constant, T it is the temperature, ln it is the natural log to the base E, P2 final pressure and P1 initial pressure. Okay. P1 it is the initial pressure, P2 final pressure. Now an isothermal and reversible process is carried out as follows. The first step here, by means of wall permeable to A, 1 mole of A is transferred isothermally and reversibly from the first vessel to the second. The initial pressure is PA and final pressure is P dash A, so that the change in free energy of the substance A is given by here delta GA, it is equal to RT ln P dash A upon PA. Similarly, when 1 mole of gas B transferred in the same direction, that means from box 1 to box 2, the free energy change is given by delta GB, it is equal to RT ln P dash B upon PB. Okay, and uh, now suppose that as gas B and A are transferred in one direction, at the same time 1 mole of gas C and D transferred isothermally and reversibly in the opposite direction. That means from box 2 to box 1. Then the free energy change, it is given by delta Gc, it is equal to RT ln Pc by P dash C, because Pc it is the final pressure and P dash C it is the initial pressure. And in case of gas D, when we transfer 1 mole of gas D from box 2 to box 1, it's a change in free energy. We denote delta GD, it is equal to RT ln PD upon P dash D. Now, the total change of free energy is the sum of all the four terms, and hence we have here total entropy change delta G, it is equal to RT ln P dash A upon PA plus RT ln P dash B upon PB plus RT ln PC by P dash C plus RT ln PD by P dash D. Since the vessels are so large that the system remained at equilibrium, the net change of free energy at constant temperature will be 0. That is delta G, it is equal to 0. Hence, this equation we get as here ln P dash A by PA plus ln P dash B by PB, it is equal to ln P dash C by PC plus ln P dash D by PD. That is P dash A into P dash B upon PA into PB, it is equal to P dash C into P dash D upon PC into PD here. Okay, as delta G it is equal to 0, we can write the P dash A by PA ln P dash A by PA plus ln P dash B by PB, it is equal to ln P dash C by PC plus ln P dash D by PD. That is here P dash A into P dash B upon PA into PB, it is equal to P dash C into P dash D upon PC into PD. and it is equal to, here we can write this term upon this term, this term upon this term. So Pc into Pd upon Pa into Pb, it is equal to P dash C into P dash D upon P dash A into P dash B. It is equal to constant, and that constant is Kp. Here, since the partial pressures in each vessel refer to the equilibrium condition, in equation this gives the value of equilibrium constant Kp according to the law of mass action, that is the product of partial pressure of C and D is divided by the product of A and B and is constant at a given temperature. This is the equilibrium constant Kp which applies for a system involving ideal gases, and in case of solutions the equation becomes Kc, it is equal to C concentration of C into concentration of D upon concentration of A into concentration of B, where this C terms the equilibrium concentrations, and we can apply this law of mass action to any homogeneous equilibrium system. For example, here N2 gas, it reacts with H2 gas to form NH3 gas, and the equilibrium constant Kp of this first reaction, it is equal to, here NH3 concentration or pressure of NH3 raised to 2 upon the pressure of N2 gas into concentration of H2 raised to 3. Similarly, for second reaction, here CO gas, it reacts with H2 gas to form CO2 and H2, and here in the third reaction 2H2, it reacts with O2 to form 2H2. So try to write down the Kp equations or equilibrium constant equations for all these three reactions, and for the next lecture we will see the want of isotherm equation. Thank you.